I'm going to do a review for the first test in my Organic Chemistry 2 class. So this is mostly going to focus on NMR, IR, reduction, oxidation, and Grignard reactions. And it's only 9 questions, but I tried to make the questions so that they would cover a lot of things that people requested me to review. So in the first few I did in class already, but I only got to like question 3, so I'm gonna do the rest of them so you can see how I would work them. And I'm gonna try to pull out different things that will help you, I think, apply. And I'm gonna go ahead and redo the first 3, even though we already did them as a class. And I'm gonna try to pull out some things that I think will help you, process through a lot of different things that we've covered. So the first one, this first part right here, this is from chapter 11, and it's converting alcohols to good leaving groups. And if you don't know how to do that, I did post a video of just my one-day overview of chapter 11. For students who weren't in my class last semester, is pretty quick and easy chapter. A lot of it is review. There's only a few new things, but the first part is it's going to convert it into an alkyl halide, and then that's A. So the first thing we do is we just convert alcohol into bromine, and that is answer choice A. Then when we add the magnesium, something I drew, we haven't gone over the mechanism of this, but something I drew for my students is magnesium is willing to give up electrons. So you can think of magnesium as giving electrons to bromine, and then bromine leaving and giving its electrons to that carbon, making this negatively charged, and then the magnesium bromide positively charged. Then the next thing, that's not exactly right. That's not really exactly the mechanism, but it basically gets us to our Grignard reagent, which is MgBr, but it acts more like an ionic bond, and it makes that salt, where the carbon is negative and the MgBr is positive. So that is B. And then C, we add an epoxide. And something I talked to the class about for making the epoxide is when you have an epoxide with something basic, what side of the epoxide is it attracted to? And an easy way to remember what side it will be attracted to is BLAM, base least, acid most. But then I pulled out even more, why is the base attracted to the least substituted side? So this is negatively charged. We haven't added the acid yet, so don't worry about that. We just stopped at B to C is the only thing we're looking at. So it is negative, so that means it does act as a base, and it's attracted to the less substituted side. So that's this side. And there's 2 reasons for that. I just realized that I wanted to say at the beginning and I didn't. The best way to do these practice problems is to try them on your own. And if you haven't tried them on your own, really doing them first and then seeing if you're getting them right is a better review for you than trying to just follow along. That doesn't really show you what you know. So it's better for you to try it out on your own. So I asked my students what they thought. And in both classes, they talked about how this is negative. I'm going to change the color because, I can't change the color on this. That seems crazy. Oh, well. Okay, so they both talked about how this is negative, and so it's going to be attracted to the less substituted side because of there's less bulkiness, right? Like these carbons are big and bulky, and so these electrons are going to be repelled by these carbons, so it won't attack there. And that's true. That's called a steric effect. So because of the steric hindrance, there's too much going on that the negative charge is not really going to be able to fit in on this side. but then negative charge will fit in on the other side. So that's one thing. The other thing is that we want to think about the inductive effect. So this oxygen is electronegative, so it's pulling electron density away, which leaves behind two partial positives. And although the pull from the oxygen is the same on this side, the then partially positive carbon can start to pull electrons in from the carbons around it. And so that makes this part right here just, it has more options to get electrons. So that makes overall the partial positive on the less hindered side greater than the one on this side. We're just getting some electron density. So there's also this electronic effect from the dipole moment and the inductive effect of these carbons acting as donating groups. Okay, so now I'm going to erase all these arrows and just do the mechanism. Oh, and one thing I wanted to also pull out is the mechanism. Some people asked me to review that. So the mechanism is basically just showing how these electrons move. And so this mechanism is saying these two electrons are going to be attracted to this carbon right here, and they're going to make a bond with it. But then this bond is going to break, and the oxygen is going to get 2 more electrons. And actually, the oxygen already started with 2 electrons. So as a result, we end up with our O, and the O has its 2 electrons, but it gained 2 more, and so now it has a negative formal charge. These 2 methyls don't move, but then this carbon on the other side has a new bond, and that bond came from, it's green because it came from the 2 electrons in green over here. So that is our answer to question C. And then very last, if we add acid, OH, and then it would look like this. And the curved arrows for this, I'll show you that as well, is the electrons, the acid is crossed out from earlier when I was saying you don't have to worry about it for C, but to get to D, you do have to worry about it. So these electrons will be attracted to that hydrogen, and I'm just going to write H+. If it was H3O+, we'd have to have them written out like this, and then it would take the hydrogen and leave that behind, and it would also generate water, so it's kind of the same either way. And so that gives us our final structure of oxygen bonded to hydrogen, and then with all these carbon chains around it. So that is the last structure, structure D. Okay. So the next question, what is the product A that would be obtained from the following reaction sequence? So the first part is the same basic idea as the last one. We're replacing our alcohol with bromine, and then we add lithium, and so it basically becomes this negative carbon. A lot of y'all got to that with no problem, but we have bromine and then we add lithium, so it's this, and then basically LiBr minus is how, or plus, and then the carbon minus. And then we add the acetone, and a lot of people got stuck here. But this reaction, well, before I draw the arrow, I'll say we have something negative over here. So if we have this negative thing, usually it's looking for something positive to react with. So if I'm then going to come over here and look for something positive, then you have to ask yourself, where is there a partial positive, or where's the strongest positive here? And we know that there's a resonance structure that makes it look like O minus and then this plus right here. And so there is a strong partial positive that's always present in carbonyl compounds. And so that strong partial positive that we saw was attractive to reduction reagents is also going to be attractive to Grignard reagents. So the mechanism that I'm doing here for a Grignard or an organometallic reaction is the exact same if we had H- as our nucleophile instead. You know, it does the same kind of thing. So I just wanted to draw out that comparison. And so if that reaction happens, then we will get our oxygen, already had 2 lone pairs on it, and it had a methyl group over here. And a new bond forms from these purple electrons to make a structure that looks like this. And then these came up here, and this is negatively charged, and then this again just acts as H+, and so that attacks the acid, and our final structure looks like this. Nope, like this. But I had people in both of my classes say, okay, this is what I got, but it looks weird. I don't see that in any of these answer choices over here. And the first thing I'm going to say is, okay, it might not immediately be obvious, but you can just check and make sure that it's there. So first of all, we know it's not C or E because there's no double bond in the structure we drew. And what I'm going to do is just number my carbons, and I'm going to start with the alcohol. So the alcohol is on carbon 1 along with 2 methyl groups, and then 2, 3, 4, 5, 6. So that's the parent chain. It's hexanol. Hexane with an OL at the end, so we make that hexanol. So I'm going to just count and see which ones have hexanol. So this one has, we start here with carbon 1. 2, 3, 4, 5. There's not hexanol, so it can't be 1. Okay. 1, 2, 3, 4, 5, 6. Okay, that's an option. 1, 2, 3, 4, 5, 6. That's also an option. So it could be either of those. Now we look, and on carbon 1, we have an alcohol and 2 methyls. On this carbon 1, we have an alcohol and only 1 methyl, so it's not that one. But so let's look over here on carbon 1. We have an alcohol and 2 methyls. And then on carbon 2 here, we have this ethyl group. And on carbon 2, we have the ethyl group. So this is our right answer, answer choice D. So don't let yourself get freaked out if it doesn't look exactly the same. Sometimes it won't, and that's okay. And then this next part, what I did is I just asked, okay, so now what would be the main difference in peaks, in the IR peaks between the ketone and your final structure, which is an alcohol? I think it's actually like that. So the biggest thing is you'd have a peak around 1710 for the carbonyl group. And then over here, instead of that, it'd be above 3,000. I think it's maybe around 3,500. I don't have the chart handy. You will have the chart, though, on your test. And then the other thing we'll see is that this peak is narrow and this peak is broad. And one of my students asked, what does narrow versus broad mean? So I'll draw it here. If I'm looking for a narrow peak, it's going to look like this, whereas a broad peak kind of looks like that. So it really is about how wide it is the big difference that you can expect to see. So that one would be narrow, that one would be broad. For both of them, we would still be able to see the CH bonds. There would just be more of them here because there's more over here, and there'd probably just be a few over here. And the CH bonds are also above 3,000. I don't know exactly where they are. Greater than 3,000 for both of these. So the big thing with IR is identifying functional groups. And being able to tell where do they appear and what will their shape be. And the other thing I wanted to point out is, so this question had nothing to do with IR, the one before. It was a Grignard question, but we made it about IR. And that's something that you can do too, is if you want to practice, you can do this by like asking yourself more questions, not just like, did I do the question that it asked on my multiple choice, but like, can you go further and test your knowledge in other ways? Okay, so both my classes, that's roughly where we got. I know it seems crazy to spend that, like a whole class period on just 3 questions, but we talked about so much. We talked about mechanisms, we talked about epoxides, we talked about electronics of like why epoxides are attractive versus not. We talked about sterics, we talked about IR, and then we also talked about Grignard reagents and the reaction mechanism for that. So there's tons of things that we talked about in just those 3 questions. Okay, so the next one is, what is the structure of the compound of the following NMR if the molecular formula is this? And then our relative integration is shown. I don't know why it cut off the, like, there's a thing down here. Oh, wait, did it also cut off the actual shapes? It did. Weird. I don't remember what they were. I know that's a question that y'all asked a lot about. So let me just look on my computer and make sure that I draw them in right. Okay, I have it on my phone. I don't know why I couldn't see it on here, but so I'll just draw this in for you. So this integral to 2 is a quartet. The integral, this tall one, is a singlet. And then the 3 right here is a triplet. So, actually I feel like, let me draw it like this. Quartet, singlet, and then this is a triplet. I do that triplet bad because they're kind of symmetrical. Okay, so the first thing I'm thinking is there's not very many peaks here. I always first look like, I cut off around 5, and anything above 5, you can have some characteristic peaks over here. Like 10 is aldehyde, and 12 is carboxylic acid. 6 to 8 is usually double, triple bonds. If there's a hydrogen off of them, double or triple. And then, or aromatic. And then below 5, things are a little bit dicier. A lot of, we call them aliphatic or just plain carbon chains are going to end up in the 4 to 5 region or the 1 to 5 region, depending on what they're next to. So, that's one thing that I noticed is there's no characteristic peaks. So there's not going to be hydrogens off of any of those types of functional groups. So that's interesting to note. The next thing I look at is we have C8H14. So we should have 14 hydrogens. And when I'm looking at this, we have 9, 10, 11, 12, 13, 14. So there might be symmetry, but we have all the hydrogens accounted for. Then I look at these individual peaks and I'm thinking, okay, this is a singlet. So we have 9 singlets, and that is hard to get anyway except for a tert-butyl group because all 3 of these hydrogens are experiencing the same electronic environment. I can draw them in. They're all experiencing the same electronic environment, and they don't have any neighbors, which is the only way that they're a singlet. And this would be bonded to another R group. So there's no hydrogens there. So there's 9, all a singlet. That is a good hint for me. The other thing I'm seeing is when you have 2 and 3, and the 2 is a quartet and the 3 is a triplet, that always means ethyl. Because we have 2 hydrogens here. I'm just drawing little dashes. I didn't want to write every hydrogen, but these are not methyls, so I'll just go ahead and write them in. So that is like, in general, ethyls show up where this one that integrates to 2, but it has 3 neighbors. So 3 is your N plus 1 equals 4. Yes, your N plus 1, where N equals 3, is 4. So a quartet with 4 and a triplet that integrates to 3 because it has 2 neighbors plus 1 equals 3. That is characteristic of an ethyl. And so I'm looking for an ethyl, and I'm looking for a tert butyl group to be present. And then the other thing I'm thinking is these aren't near each other. So like these aren't impacting each other at all. So it could just look like this, where we have the ethyl on one side and the CH3 on the other. And because there's this carbon right here with no hydrogens, it doesn't impact anything. But I'm going to count up my carbons and see if that makes sense at all. So I have 1, 2, 3, 4, 5, 6 carbons. Okay, so no, that does not make sense at all because I'm missing 2 carbons. So that puts me in a little bit of a predicament. I'm going to go over here to my answer choices because I have that as an option, and I'm going to look at what I have. So this does not have the tert butyl group, so I'm going to get rid of that right away. This also doesn't have a tert butyl. If there's a hydrogen, there's a hydrogen right there, an implied hydrogen. That hydrogen would be an integral to 1, and it would be a septet, but we don't have that, so no. Now this, and this all have my tert butyl group, so those are all good options. And then this one has my ethyl, and this one has my ethyl. This one has my tert butyl, but it doesn't have an ethyl. These 2 hydrogens and these 2 hydrogens would split each other, and they would both be, it would be integral to 2, and they would both be triplets. And we don't have that. We have a 2 that's a quartet and a 3 that's a triplet. So now we're looking at this. One big flaw I see in this one is there's 2 more hydrogens here. And with those 2 hydrogens, we don't have peaks for those. We only have peaks for these 3 and these 2. So I don't think it's B, or sorry, that one's C either. So our last option right here is D, and that should be our right answer. But just to double check, I'm going to say, okay, our 2 carbons right here, great. And then we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. And then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 hydrogens. And I like to double check and see, like, would this make the peak that we expect? Well, we know a triplet with no neighbors, or sorry, a tert butyl with no neighbors is going to make that peak. So I like to label it. So if this is peak A, B, and C, the A for the triplet makes sense here. The B peak is the A for the tert butyl. I keep saying triplet instead. The B for the ethyl, the CH3 on the ethyl is right here. And C is the 2 hydrogens that have 3 neighbors for a quartet. So that's one way to do it. Another way to do it that we haven't talked about yet, so I'm going to completely erase all this. This is one option for you, one way of thinking about it that I would say is like, you're sort of like solving the puzzle, and you're seeing some characteristic peaks that you're recognizing. That's one way of approaching NMR. There's another way of approaching NMR. Oh, I forgot that I had to draw this back in here. So this was a quartet. So you already know your answer, but I just want to show you this other thing. And you should have learned it in your lab class. But that thing is the index of hydrogen deficiency. So normally, if we have a carbon chain like this, we have 1, 2, 3 carbons. We have 3 carbons. And our hydrogens are 1, 2, 3, 4, 5, 6, 7, 8. So pretty consistently, your hydrogens are going to equal the number of carbons times 2 plus 2. So 3 times 2 is 6 plus 2 equals 8. So if we have 3 carbons for a totally saturated carbon, it's going to be 8. But if we had a ring, we don't have those 2 end groups, so we only have 2 hydrogens for every carbon. So now we have our number of carbons equals 5. 1, 2, 3, 4, 5. So you would expect our number of hydrogens to equal 5 times 2 is 10 plus 2 equals 12. But it doesn't. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, I forgot to dip my dot on those. Let me redo that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So there's 2 hydrogens that we don't have that we would normally expect to see. So the index of hydrogen deficiency is 1. Usually you get that effect where there's 2 less hydrogens with either double bonds. Triple bonds have 2 index of hydrogen deficiency, or rings equals 1 index of hydrogen deficiency. I don't usually think of doing that first because I'm so used to looking at the spectra and figuring out what the peaks are. I just wasn't taught to use this first, but it is a really good tool. And I think you were supposed to have learned this in your OChem lab class already. And so if you did, that can be something that helps you. One of your classmates told me they always use that approach, and I was like, oh yeah, that's a really good one. So if we did that approach here, still the first thing I look for is significant peaks. Do we have any significant peaks? No, we don't have any. Everything's below 5, so these are all probably just plain carbon chains. So then the next thing we can look at is the index of hydrogen deficiency. So we have 8 carbons times 2 would equal 16 plus 2 equals 18. But we don't have 18 hydrogens, we have 14. So we'd expect 18, but we only have 14, which means we have 4 missing hydrogens, basically. So that means we have 2 index of hydrogen deficiency, or another way of saying that is we have 2 missing hydrogen pairs. And those come from rings or double bonds, right? So that would give you 1. So if we could have 2 rings, we could have 2 double bonds, or 1 triple bond is 2 index of hydrogen deficiency. So that would have given me a really helpful clue when I was thinking about the fact that, like, oh, we need to have 2 index of hydrogen deficiency. All of these do have 2 index of hydrogen deficiency, so it doesn't give a good clue on looking and eliminating multiple choice, but it does tell me what could have been going on between these groups. So still, I know that, I'm going to get a tert-butyl group on one side and I'm going to get an ethyl on the other. I'm looking at that and realizing that I'm short 2 carbons, but I have all my hydrogens already. The only thing that could really connect this would be a triple bond. So that would have sort of given me a clue without having to have the answer choice. You don't have to use that. I like to just look for significant peaks and sort of process through what it could be. But if you get stuck, that could be a good option for you. Okay, the next question for the following reactions, suggest what would accomplish them, then draw the mechanism. Okay, to go from a ketone to an alcohol is a reduction reaction. So hopefully you first ask yourself what type of reaction this is. This is a reduction reaction. So we have 2 different things that can reduce, LAH and NABH4. And Simi had this great idea in my one of my classes where, you have cake, right? So you have cake, and cake is carboxylic acid, so COOH for carboxylic acid, or you could write out carboxylic acid, I guess. Carboxylic acid, aldehyde, ketone. It's hard for me not to write the letter that comes after that. Or ester are the big things that get reduced. Cake gets reduced by LAH, but if you have NABH4, you can't take the whole cake. It can just take a slice of cake. So if you want a slice of cake, aldehyde or ketone, you use NABH4. Now, the way I've always remembered it is just that Aldehydes are easier to reduce than ketones, and then we have esters and carboxylic acids. And so NABH4 can only reduce these two, but LAH can reduce all of them. That's another way you can remember it, whatever makes most sense to you, but I thought this was really cute, so I wanted to give them a shout out and say, oh, thank you so much. So, yeah, I love that idea, and I've seen other students use it, and when she told me about it, she was like, did I eat? And I was like, you ate. That's amazing. So, that made me so happy. Okay. Next, so I was going to say, we know it's a reduction reaction, and we know that we can use either LAH or NABH4 for reduction. Our starting material is a ketone, so either works. We can use NABH4 or LAH, it doesn't matter. So I'm just going to pick one, lithium aluminum hydride, and this is going to go here, and this bond is going to break and go up, and we will get an O minus. And then we ask ourselves, okay, always after our initial nucleophilic addition to this carbonyl, what happens next? Can our carbonyl recover and kick out a leaving group? There's no good leaving groups here. So then we would have to add acid, and that would get us to our final product. So for this one, I do want to say, suggest the reagents. The first reagent would be either LAH or NABH4, and then the second one would be H3O+. So make sure that you're adding an acid of some kind, or it could be any acid, it doesn't have to be H3O+. Okay, and then the next one is, first I'm noting that there's a double bond that nothing happens to. And then I'm noting that there is an ester that seems to also be reduced. So there's an ester, which means we can use only LAH, right? Because NABH4 takes a slice of cake, it leaves the E behind. So if we have the same starting material, lithium aluminum hydride, our hydrogen will attack, and this will come up, and we get O minus. Then this bond comes back down, and it can kick out our leaving group. So, and I don't always draw the hydrogen in, but the hydrogen that attract formed a new bond there. It also made it up here. I didn't draw it, but there is a bond to that hydrogen here too. And so our new thing would be an aldehyde. And then this aldehyde could again be attacked by the lithium aluminum hydride. And we get H, O minus, the new H that attacked. And so we could use lithium aluminum hydride, and then if we add acid, that would become an OH. And it might look different if you're like saying like, oh, well, this is in a straight line and mine isn't. Again, let's just number the hydrogens in C, the carbons in C. So we have 1, 2, 3, 4, 5, and then the alcohol, 1, 2, 3, 4, 5 carbons, and then the alcohol. So the alcohol is just in a different spot, but it does still work. So the to answer the question of the reagents, again, you would use LAH and acid. The only difference between these two is you could have used 1 NABH4 and then 2 acid. Okay. For the following reaction, suggest reagents you would choose to accomplish the following transformation. Why did you choose the one you chose? How would this be different if it were primary alcohol? Okay, so this again is like multiple questions in one. So the first one, I'm seeing that this alcohol is going from an alcohol to a ketone. Sorry, I just realized that my battery is running low. Oh no, I'm still good. Okay, so this alcohol goes to a ketone, and so that is an oxidation reaction. But there's also right here a double bond that is unaffected. That matters. because our three reagents that we can use for oxidizing are Jones, KMNO4, or PCC. And so looking at these, Jones will take a primary to a carboxylic acid. KMNO4 will do the same thing, but it also breaks up double bonds. It's a pot stirrer. It stirs the pot. It causes drama wherever it can. And by drama, I mean oxidation. And then PCC takes a primary alcohol to aldehyde. All of them will take a secondary alcohol to a ketone. So all of them will do that. So we could do Jones, KMNO4, or PCC for this, but we can't do KMNO4 because it would also break this double bond. So I would use either Jones reagent or PCC to accomplish this. Either one of those should be fine. Now, the next question it asks is how would this be different if it were a primary? But I want to ask how would this be different if you used KMNO4? So what would your product be basically? So when I think of what KMNO4 does to double bonds, I think of it splitting them in half and literally adding an oxygen on either side. So this would be, and then the hydrogens here initially stay. You can think of them as initially staying, and we've oxidized our alcohol, but then it would oxidize it even further, and your aldehydes, our aldehydes always become carboxylic acid with KMNO4. So let's see, 1, 2, 3, 4, 5 carbons. So your final answer would be 1, 2, 3, 4, 5 carbons with carboxylic acid on either side, and on carbon 3, 1, 2, 3, a ketone. So that's a way to stretch your thoughts further. Another thing is if this were a primary alcohol, you could only use Jones reagent, because if it were a primary, you could, only use Jones reagent. Jones reagent will take it to this without affecting the double bond, but PCC would stop at the aldehyde, so you would get different results from those. I just drew a carboxylic acid when I said aldehyde, but aldehyde looked like this. So that's why I chose the one I chose, and that's how it would be different if it were primary alcohol. And we added a bonus question of what would happen if it was KMNO4. Okay, Jones reagent will fail to give a positive test with which one of these? So basically, which one will it not react if it's not going to give a color change with? Jones reagent will take primary alcohols to aldehydes and then to carboxylic acids. And it takes secondary alcohols to ketones. It doesn't do anything with tertiary alcohols. Hopefully you remember that. Because, there's no hydrogen that you can eliminate from the right there, which is what is the mechanism for these, is it takes this hydrogen basically from the beta position, from where the carbonyl carbon would form. So that's what I'm looking for, is which one of these is have a primary or secondary alcohol. So we're looking here at the alcohol. We look at the point of attachment, and it's attached to two things. So this is a secondary, so that would work. This alcohol, the point of attachment, we look at that point of attachment. So this is a primary, so that would work. This is an aldehyde. So this is, it would work. This is an aldehyde, and aldehydes get further oxidized by Jones reagent to carboxylic acid. I almost wrongly caught that off. What was I going to say? Almost wrongly got the wrong answer. Caught me off guard. That can also be oxidized by Jones reagent, so this would have a color change. And then last but not least, this has 1, 2, 3. So with those 3, this is a tertiary, so this would not be oxidized by Jones reagent. Okay, what is the product that would be obtained from the following reaction? So the first step, we have, draw this down here. The first reaction we have a carbon-carbon triple bond with a hydrogen, and we have CH2, CH3, MgBr. So that basically looks like this. And I wanted to use this question to talk about how Grignard reagents can't be used with anything more acidic than an alkene or an alkyne. So alkenes have a pKa of 44 and alkanes have one of 50. So anything that has a lower pKa, if it's less than 44 or 50, if it's more acidic than these, then immediately the Grignard is going to react. And I got a lot of questions about this, and this is the same reason it doesn't work with protic solvents, is if you want this to be your Grignard, then this Grignard is immediately going to react with this hydrogen for an acid-base reaction, and it's going to leave the electrons behind right here, and you would get this. Because the pK of that hydrogen is 25, so it's pretty acidic. And your Grignard has now just become ethanol. We went from CH3, CH2 to, with a negative charge, to, it took that hydrogen. So, and maybe it'll help if I draw this out where it's we actually have the CH3 so that you can see where the new bond is formed. CH3, CH2 with a lone pair on the carbon. The new bond is formed. So when that new bond is formed, it becomes CH3. You know, we still have the two hydrogens and a new hydrogen is formed right there. So this lone pair right here from your Grignard took this hydrogen and made a new bond right here, which means now this is no longer your nucleophile because this doesn't exist. And now this is your nucleophile. So the same thing will happen if you use a protic solvent with a Grignard reagent. Okay, so now we're back to epoxides. These are equally substituted, so the nucleophile will attack on either side. It doesn't matter. So it'll attack to either side, and we will get, I just picked one, O minus, a CH3, and then a bond from these electrons right here. There's a new bond to that. Here, it was actually this one right here. These electrons made this new bond. The CH3 was already there from this structure. And there's a carbon-carbon triple bond. And then that is bonded to a benzene ring. Okay, so that looks bad, but hopefully you kind of see where that structure came in. I can redraw it a little bit better, but... So our epoxide opened up. We got O minus from this bond breaking. This CH3 was already there, and this CH3 was already there. And now our O minus is from that bond breaking. But there's also a new bond from these purple ones right here. So that lone pair is where that came from. And then we got our benzene ring. So this is our final structure. And so I wanted to point out that this is like a technique that's sometimes used, is where you put a Grignard with something more acidic, but it also is sometimes tricky to students to realize what happened here. It's like, wait, I thought this was my Grignard reagent. It's just the same as you've seen before. So whenever you see it, draw out the negative charge and think about where it will attack. So let's see. Now I'm going to number, oh, well, this would also, we add acid for the last part, so this would become an alcohol. Okay, so I'm going to number my carbon chain starting with my alcohol. We have 1, 2, 3, 4, 4 carbons, and then the fifth one is where it bonds to the benzene ring. So this has 1, 2, 3, 4 carbons, but it doesn't look like it ever reacted with the epoxide, so I don't think that's right. Let's see. This doesn't have an alcohol. That's an easy way to get rid of them, is which ones have an alcohol. This one does have an alcohol. This one doesn't have an alcohol, and this one doesn't have an alcohol. Oh, wait, yeah, that one does. Okay. So it can only be, let me erase this so that it's not in the way. It can only be either answer choice D or C. And so now we're going to figure out which one is it. Is it answer choice D or is it answer choice C? So we are going to count our carbons, starting with our alcohol. 1, 2, 3, 4, and the fifth one is where the benzene is. But then we have this thing over here, which we don't have in our other one. I think they're trying to trick you if you didn't know that the Grignard would react and make that just the ethane. So now we'll come over here, 1, 2, 3, 4, and the fifth one is where the benzene attaches, so that's great. And at carbon 1, we have the alcohol, and we have a methyl, and at carbon 2, we have a methyl. So answer choice D is our right answer. Okay, the last question, I have enough battery, great. The last question is I'm going to do this last one, but I also kind of want to do like how I would make a review sheet if I were you and like a recommendation of how to study. But so you might want to skip forward to that one, or you can pay attention to this one if you want. Okay, so a molecular formula with the compound C9H10O2 has the NMR spectrum shown. Which of the structures given is consistent with this spectrum? So I mentioned before, I kind of look at anything above 6 to see what's important or like if there's any distinct features. And I'll say that this looks like an aromatic ring or an alkene. It's in the 6 to 8 region. And this, I'm confident, is a carboxylic acid. So I'm just going to go ahead and say I definitely have a carboxylic acid, and I definitely have some double bonds happening here. Okay? And then down here, I have 2 multiplets. It doesn't have what these integrate to. I don't know why it selectively cuts things off on here. That's annoying. It's not on my phone either. Okay, so what I can do, I don't have what they integrate to. I can kind of tell what their splitting is, but not super well. So I'm going to see what I can do from here. First, it looks like all my answer choices have an aromatic ring. So that 6 to 8 is probably my aromatic ring. And then this aldehyde, so not a carboxylic acid, and this is not a carboxylic acid, and this is not a carboxylic acid. Oh, look, I panicked for no reason. You didn't even need all that information. But before I commit to this, I'm going to make sure it's C9H10O2, C9H10O2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, 2 oxygens. I'll do a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Great. Okay, so that's right. You can also do the index of hydrogen deficiency on this one. We have 9 times 2 equals, 18 plus 2 is 20. So you would expect that you would have 20, but we only have 10. So there's 5 index of hydrogen deficiency here. So a benzene ring by itself, because it's a ring, that's 1 index of hydrogen deficiency. And then 1, 2, 3, that is for the 3 double bonds, 3 more. And then if we know we have a carboxylic acid, that double bond is the 5th. So it matches our index of hydrogen deficiency. So one thing that I guess I just want to make sure that y'all know everything that you need to know. And this was a suggestion from another one of my students, so shout out to her during office hours. And what I kind of recommend you do for a test is go through and what is everything that we learned. So from chapter 9, we did IR and we did NMR. And for IR, we looked at the shape, the intensity, and the location of the signal, and each of those told us something. So the shape told us broad versus narrow. We know that is if the presence of hydrogen bonding, and hydrogen bonding is not a bond. So make sure that you know hydrogen bonding is intermolecular force, and I did a whole video just yesterday for my OCHEM 1 class about that. And then intensity is how polar. And location is what is it? What is the bond? And we know that below 1600 we don't care about. That's the fingerprint region. Above that, usually there's a really nice chart that kind of breaks it up that like around, 2000 to 16 is like double bonds. And yeah, so you can kind of know the general location, but I'm going to give you a chart. For NMR, we learned about the shape. So that's I started to write splitting halfway through. Shape is the splitting. So the singlet, doublet, triplet. We learned about the location. The location has to do with how many electrons are around the hydrogen. Electrons around the hydrogen. And if we go to the left towards 10, that means there's less. So it's usually bonded to something pretty electronegative. If we go to the right, there's more. So usually this is like where the alkanes hang out, and this is where things that are missing a lot of their electron density, like carboxylic acids and aldehydes, hang out. So, and the shape and splitting, that has to do with the neighbors. I forgot the most basic is the number of peaks has to do with the number of unique environments. The number of peaks. And then the integral, or the intensity, the area under it, is equal to the number of hydrogens at each location. Okay. And then you can do the same thing with Grignard reagents. So what did we learn? I guess the next thing we actually did was redox. So redox, we learned, 3 different oxidation reagents. PCC, I already did a little overview of these, KMNO4 and Jones. And then reduction reagents. We learned LAH and NABH4. I already did a little overview of those as well. You need to know the mechanisms for these. And then redox. Then the last thing we did was Grignard. So like, how do we make a Grignard? We go from the carbon chain. Needs to be an alkyl halide. And then add magnesium, and then how do we react it? And we've seen them react with carbonyl groups, and we've seen them react with epoxides, and we've seen them react in acid-base reactions. And I know that doesn't seem like a lot, but that's pretty much all that we've learned. And so it doesn't seem like a lot, but it takes a lot to think about every one of these little details and get used to doing it. We also make sure you're familiar with Chapter 10, addition reactions, and adding alcohols. Or adding water across double bond. Because we build on that a lot, and epoxides, chemistry. I said Chapter 10, but that's actually Chapter 11, sorry. So make sure you're familiar with what we talked about for Chapter 11. That when I posted, you also should know these things. And then last but not least, we talked about retrosynthesis, and retrosynthesis is really focused on this technically is retrosynthesis that we did right, where were they? These were retrosynthesis questions where you had to recommend the reagents. So how do we get from point A to point B? Okay, I think that's everything I wanted to cover. I hope this was helpful to y'all, and good luck studying for your test tomorrow.